Good morning, champs. When a hot object cools down, where is the main resistance to heat flow? Inside the solid or at the surface between the solid and the surrounding fluid? The answer is hidden inside the Biot number. Today, we derive it from scratch using dimensional analysis and a Gauss-Jordan tableau. Assume heat transfer depends on three variables: the heat transfer coefficient, a characteristic length, and the thermal conductivity of the solid. We denote them as H, L, and K sub S. First, we convert each variable into SI base units. The heat transfer coefficient has units of watts per square meter Kelvin. A watt is a joule per second. A joule is a Newton meter, and a Newton is kilogram meter per second squared. Therefore, 1 watt becomes kilogram meter squared per second cubed, and the heat transfer coefficient becomes kilogram per second cubed Kelvin. Thermal conductivity has units of watts per meter Kelvin. Substituting the watt unit gives kilogram meter per second cubed Kelvin. Length simply has units of meters. Now we assume a dimensionless group consisting of h raised to a multiplied by l raised to b multiplied by k sub s raised to c. Substituting the SI units and collecting exponents gives 4 equations. Now we build the augmented Gauss-Jordan tableau. Using the first row as the pivot, we eliminate the matching terms below it. After performing the row operations, 2 rows become 0 rows. This tells us that those equations were dependent and did not add new information. The reduced tableau gives a equals negative c, and b equals negative c. The variable c is a free variable. Choosing c equals negative 1 gives a equals 1 and b equals 1. Substituting these exponents back into the dimensionless group. This is the Biot number. The Biot number compares internal conduction resistance to external convection resistance. If the Biot number is low, heat moves through the solid very easily and the temperature remains nearly uniform throughout the object. If the Biot number is large, significant temperature gradients can develop inside the solid. The Biot number therefore tells us whether we can treat a solid as having one uniform temperature, or whether we must solve the full internal heat conduction problem.